Hello and welcome to NCC Group's Cryptopals guided tour. My name is Eli, I'll be your guide. In this video we're going to be looking at challenge 6 from set 1, which, as you can see here, involves actual error-prone coding. So unlike the previous challenges apparently, this one is the qualifying challenge. Let's see if we can qualify. Let's take a look at what we have to deal with here. There is a base64 encoded encrypted file. It has been encrypted with repeating key XOR. And as we saw back in challenge 5, repeating key XOR is just like single byte XOR, except you rotate through a series of bytes, repeating after you reach the end of the key. In this challenge, having implemented that, we are now going to try to break it. There's an algorithm given here that we will follow fairly closely. We will start out with implementing the Hamming distance function. The Hamming distance will be crucial to guessing the size of the key that we are looking at. And once we know the key size, we can break the ciphertext into blocks of that length and then essentially treat it as a set of single byte XOR ciphers. Because we know that for every one of our blocks, the first byte in it is going to be encrypted under the same key byte. The second byte in each block is going to be encrypted under the same key byte, and so on and so forth. So we can essentially transpose them and crack them individually. Then once we've cracked them individually, we can reassemble those solutions to reassemble the full key. Now, nothing in here is impossible per se, but it is slightly challenging. So I'm going to try to go slow and talk you through every step in the process. We'll start out with implementing Hamming distance. Now, the Hamming distance is a fancy word for the number of bits that are different between two bit strings. And the easiest way to compute that is through a related function called the Hamming weight. The Hamming weight of a bit string is the number of 1 bits in it, the number of bits that are set to 1. So if you had, for example, a bit string like this, the Hamming weight of this would be 3, because it has 3 ones and 2 zeros, although the number of zeros, I guess, depends on how large you consider this to be. If this were an 8-bit value, then it would have a bunch of leading zeros, but that's irrelevant here. So essentially, if you want to compute the Hamming distance between two strings, what you can do is you can take the XOR of them. The XOR, bear in mind, is going to be 1 whenever precisely one of the input bits is 1, and it's going to be 0 if they're both 1 or both 0. So the XOR of two strings is going to have a 1 bit on each differing bit, and so the Hamming weight of the XOR is going to be equal to the Hamming distance between two strings. This might be a little clearer if I show you the actual code. I'm going to show you 5 reasonable implementations of how this Hamming weight function might work, and then we're going to benchmark all of them and see how they fare. Now, you might say, why am I showing you 5 implementations? The answer is because there's a heck of a lot of ways that you can do this, and each of them is suitable for different contexts. And so I think it's valuable as sort of a learning exercise to take a look at all of them and discuss them as we go. So the first one is extremely straightforward. It uses this bin function that essentially returns you a string representation of the binary expansion of an integer. So you can essentially take that binary representation and then count the number of 1 substrings within that string, and that will give you the Hamming weight. And we're looking at single byte inputs here, and I'll explain why later. But essentially the idea is that if you can compute the Hamming weight of a single byte, then you can iterate over all the bytes in a byte string and call this on each one of those in turn to get the full Hamming weight of the byte string, and then we can combine that with our bytes XOR function that we've already written in order to get the Hamming distance between two byte strings. So I guess I won't explain that later, I just explained it now. But anyway, moving on, here's our second Hamming weight function. This one applies a single bit mask to the lowest bit within the byte, and then after doing that, shifts the byte over by 1. So let's look at this by example. I'll open a third terminal here so that we don't lose our code view. If we had, we'll take our example of the byte 22 once again. 22 and 1 is 0 because the lowermost bit in 22 is 0. But then if we shift 22 over by 1, we get 11, which has a 1 in its lowermost position. So 11 and 1 is 1. And we shift that over, we're going to get another 1, 0, 1. So essentially what this loop does is it keeps shifting this bit string over by 1 position until we've essentially shifted it out of existence. Because if we go 11 shifted by 1, then You can see we lose the trailing bit on that. And then again, we lose another one. And you can see that eventually this process is going to end up with the number being equal to 0, at which point we terminate the loop. So this algorithm is effective with small bytes, which can be expected to have lots of leading zeros. And it's also just sort of good in general purpose. It generalizes to larger integer formats than just a byte, which is nice. It doesn't rely on converting anything to strings, which is also convenient, although the cost of this might be lower than you might expect it to be. And we'll benchmark this to see how it performs momentarily, but I have a few other functions to show you before we do that. Here is the third way we might reasonably implement this, and this one, to borrow a phrase, you are not expected to understand how this works. But here it is. And this one is really quite cool. So we're going to take a moment to try to explain this. I'm not sure how good of a job I'm going to do. All right, and this is Eli from the future, cutting in to try to give a better explanation than I just gave off the cuff. While I did my best trying to explain this on the command line, it probably wasn't as clear as I wanted it to be. So I'm going to take another crack at it, aided by this advanced visualization software known as LibreOffice Calc. So here we have the algorithm. Here we have the binary representations of the constants used. And then here I'm going to illustrate the steps in the algorithm. So before we begin, the basic idea of this is to do a bitwise sum, because the Hamming weight is the number of 1 bits, and that is going to be equal to the sum of this bit plus this bit plus this bit plus this, and this. Because, of course, the 1s are going to add 1 to the sum, the 0s are going to add 0, and the final sum is going to be the number of 1s. And so the way we do this is by a divide and conquer algorithm. We start by summing these 2 bits together, these 2 bits together, these 2 bits together, and these 2 bits together. And the crucial realization is that the sum of 2 1 bits is going to be 10, 1, 0, which fits in the same amount of space that the original bits did. Likewise, the sum of a 0 and a 1 is going to be 1, which also fits in a 2-bit space, and the sum of 2 zeros is obviously going to be 0, which fits in there as well. So what we can do is we can compute this sum in place in a number of steps. So we're going to start by taking our byte and computing a bitwise AND against this mask OX55, which, as you can see, is sort of an alternating number. It has every other bit set to 1. So if you compute the bitwise AND of the byte and OX55, you will retain this 0 bit being 0, this 1 bit being 1, this 1 bit being 1, and this 1 bit being 1. But these other 4 bits will all be 0. 3 of them are already 0. This one will be 0'd as well. So you take that, and then you add that against the number shifted over by 1. So this is just, I took this, copied it into here, this bit, copied it into here, this bit, copied it into here, and this bit, copied it into here. And now we're going to compute these sums. And when we do that, we get 1 plus 1 is 10, 0 plus 1 is 1, again 0 plus 1 is 1, and 0 plus 0 is, as always, 0. Okay, so now this number is what we have after executing the first line of this algorithm. Now we move on to the second line, where we are doing bitwise AND against a mask that looks like this. So what this does is if you AND against this mask, then you retain the values in these positions that I just highlighted here. And if you shift over by 2 and then compute the AND, then you're essentially getting a second number that looks like this, and just pretend that these empty fields are zeros here. And then if we compute the sum here, then once again, this sum, the most it can be is if we have 1, 1 plus 1, 1, which is 3 plus 3, which is 6, which equals 1, 1, 0 in binary, which can fit into a 4-bit field. It can actually fit into 3 bits. We don't even need, we have an excess of space here. So we're going to compute this sum and put it in here. We're going to compute this sum and put it in here. And so let's do that. And this works exactly how you'd imagine. 10 plus 1 is 11, and 1 plus 0 is 1. All right, now we have the result after the second line of this algorithm. Now, the third line ands against this mask OXOF, which has its topmost 4 bits zeroed and its bottommost 4 bits set. So we're shifting this over by 4, anding it against that mask. So let's compute this sum. 11 plus 1 is 100, at least in binary. And we have leading zeros. So there we go. So we have binary 100, which of course is decimal 4, which is the number of 1 bits in our original string. So we see that the algorithm has worked. What's nice about this algorithm is that the number of steps it takes in order to compute the result is logarithmic relative to the bit length. Each step allows you to sum together twice as many bits because the size of the individual fields that we're summing together doubles with each step. And so what that means is that if we're taking the Hamming weights of very large numbers, like say 64-bit integers, then this is a very efficient algorithm to do that. It requires hard-coded constants, and so you do need to know the size of the integers in advance, or else you can, I guess, pre-compute them. But then that cuts into your runtime unless you're doing some clever optimizations, like pre-computing them for a batch of computations. So this is an algorithm that mostly comes up when you're working with very large numbers in a very low-level language, but it is still a useful one to know because for large numbers, it is far and away the best algorithm in the general case. We will see some others that work better in specific cases. Let's move on to that now. So that was a bit of a long explanation, and I apologize if that wasn't terribly clear. But that's the general gist of what's going on here. And this one actually can be optimized quite heavily. For example, this trailing AND operation is not necessary because we already know that this is a byte that's shifted over by 4, therefore its leading 4 bits are going to be 0. I just included this AND in here for clarity's sake. And there are some other ways that we can rewrite this as well. If you want to learn about stuff like that, there's a book called Hacker's Delight that will go into this in more detail than you could ever want. And I really recommend that if this sort of bitwise twiddling is interesting to you. For me, it's interesting to know about, but I think this is about the level of detail that I'm happy with. Let me show you the fourth Hamming weight. This one is also very cool. And this is one that I got from that same book that I just mentioned. This one works by counting the 1 bits through kind of a tricky strategy. All right, and here's Eli from the future back again to try to break down the bitwise logic in this algorithm. So before we get to that, we're going to start with a quick refresher on elementary school arithmetic with remembering how the algorithm for subtraction works. So if you have 20, you want to subtract 4 from it, you say, okay, we start with 0 minus 4. Well, we're in elementary school, we don't know what negative numbers are, so we're going to pretend that 0 is a 10. 10 minus 4 is 6, and then we have to compute 2 minus 1, because we've carried the 1. 2 minus 1 is, of course, 1, and we get 16, which is the correct answer. Now, this exact same algorithm works just fine in any base, including base 2. So let's go ahead and look down here when we're applying it to the number 22, which we have the base 2 representation of right here. We are going to go ahead and subtract 1 from this number. Now, what happens when we do that? Okay, 0 minus 1, we are going to make that into a 10, carry the 1. 10 minus 1 is 1, because we're in base 2. And then, of course, 1 minus 1 is 0. And then the higher bits on this are, of course, unchanged. So now we have 2 numbers here. We have this and this. And if we compute the bitwise AND of these, then what are we going to get? Well, the higher order bits are all the same between these. So that's going to be 0, 0, 0, 1, 0, 1, just fine. And then these bits have all been flipped because that's essentially the result of our subtraction operation. So these are both going to be zeros. And so what we've essentially done here by subtracting 1 and then doing a bitwise AND between the original number and that number minus 1 is we've managed to 0 the lowermost 1 bit. Remember, this bit was already 0, but this one is newly 0. And every time we run this algorithm, we can see it if we try it again. Take this minus 1, okay, that's going to be a 1, carry the 1. That's going to also be a 1, carry the 1. It's going to be a 0, 0, 1, 0, 0, 0. And then we compute the AND of these, get 0, 0, 0, 1, 0, 0, 0, 0, because of course these all mismatch. These are 0, these are 0, these are 1. Very good. So we can see that every time that we compute this line right here, we are setting the lowest most 1 bit in byte to 0. And eventually, we're going to end up setting all of them to 0, at which point byte will equal 0. At that point, the number of iterations that we've gone through this loop will equal the number of 1 bits that were originally in this value. So what we're doing is we're running through the loop and we're counting the number of iterations. And in each iteration, we're zeroing a 1 bit. And eventually, when we reach the end of the loop, when byte equals 0, then we just return the counter, because that's going to be equal to the Hamming weight. And that's how this algorithm works. And so that's quite cool, in my opinion. I actually really like this one. I think that's very elegant. And you're going to love this next one, because this, I'll just show it to you. So this is a 2-parter. Here's the first part, and here is the second part. Now, this might feel like cheating, but as the philosophers say, all's fair in love, war, and cryptography, and this is cryptography. So what we're doing here is we are pre-computing the Hamming weights of every byte. And there are, of course, only 256 possible values for a byte, so this is actually not that memory intensive. This takes up a very small amount of memory. And once we have those pre-computed, we can essentially just use them as a lookup table and query that table here. And as you can imagine, this is a fairly performant solution. So let's go ahead and benchmark each one of these. We are going to define 2 byte strings, call them A and B. And we're going to define a Hamming distance function, which takes a Hamming weight function as an argument. And for this to work, we also need to import bytes XOR. Okay, change of plan. We are going to copy in the definition for bytes XOR. And now, after that slight blip, we are prepared to run our benchmarks. So first, we'll benchmark Hamming weight 1, which works by converting to a string and counting the 1 bits. All right, and that takes 38.8 microseconds. Not bad. Let's try Hamming weight 2, which is the one that works by applying a mask to every single bit in the byte. And this one takes 108 microseconds, so this is, substantially slower than the one that works by string conversion. Hamming weight 3 is our divide and conquer strategy, which, by the way, is very useful in languages like C, which have fixed size integer types. In Python, it makes less sense because integers can technically be unbounded, but we are assuming bytes here, which of course are bounded, which is why I chose to use it here. But it is very, very efficient with larger integers because it scales logarithmically with bit length. And even in a small case like this, we can see that it's not bad. It's still not as good as our first solution, but it's better than the second one here. It's actually not performing that different of an operation from Hamming weight 2. It's just performing it in a different way through a divide and conquer strategy rather than 1 bit at a time. And that degree of parallelism is what leads to the speed up that we see here. Now let's try Hamming weight 4, which is the one that works by zeroing each 1 bit in turn. And this one actually has fairly similar performance to Hamming weight 3. Again, this one would work very well on sparse numbers, not so well in the general case. Now we're finally going to try the lookup strategy, and we can expect this one to do fairly well. And there you have it. This is the winner by a country mile. It's almost twice as fast as the next fastest option. So this is what we're going to use in our actual script, and we can feel good about that. So let's go ahead and get that script started. We'll start out by writing our function to build a lookup table of Hamming weights. And the reason that we're computing this table within a function is so that we avoid polluting the top-level namespace with variables like pow2 or k or v. We want to keep all of those local to this function so that the only thing that escapes to the top-level namespace is the thing we actually care about, namely the lookup table. And the algorithm used to generate that table is not something that anything else needs to know about. And you'll notice the naming convention here for the function getHammingWeights is prefixed with an underscore to indicate that it's local. However, weights is something that conceivably might be useful from other functions, so we are not prefixing that with an underscore. We're just making that a top-level variable. Now that we have this function, we can make sure that it produces the correct output. Well, actually, excuse me, we should define our Hamming distance function first. And this is a slightly different way of writing this function than we used in the interactive session. This essentially achieves the same result, but does it in a slightly more terse manner. Now we're going to move on to guessing the key size. Oh, we'll add an assert in here to make sure that our Hamming distance function is working correctly. All right, and our assertion passed. So we know that this is all good so far. So let's move on to guessing the key size. And I'll start a name guard block down here for all of our main program logic. So we're going to try key size values up to 40, which is the value suggested here. And we're going to do essentially what's described in these two steps here. And what this suggests for us to do at the top here is essentially to take the first two blocks, get the Hamming distance between them, normalize it by dividing by key size to get the average number of differing bits between them, and then use that as a metric for the quality of our guess about the block size. And so you might be wondering why it is that this works. This is actually a variation on a technique from classical cryptanalysis, just like the repeating key XOR cipher is a variation on a classic cipher known as the Vigenère cipher. My French colleagues are probably mortified at my pronunciation of that, but we're going to gloss past that. The Vigenère cipher is very similar to repeating key XOR, except that it uses an alphabet of letters rather than one of bytes, and it uses addition instead of XOR. Other than that, it's extremely comparable. And the cryptanalysis is also extremely comparable. We have this idea here called Kasiski examination. And again, I doubt I've got that name right, but I hope I did. The idea behind Kasiski examination is basically that if you have repeating letters in your plain text and they happen to line up with repeated letters in your key, then you will observe the same ciphertext letters, and the edit distance between those ciphertext letters in particular is going to be very low. In this case, in this example, it's 0. This is a very convenient example because you see a match of an entire block of plain text matching the key. And so you see a repeated block in the ciphertext, which is, of course, atrocious. I don't believe that we have anything quite that egregious in the Cryptopals problem, but we do have a number of repeated plain text characters lining up with the same indices relative to our key, and that is something that we can detect by taking edit distances. So anyway, that's enough talking. Let's get to actually writing this thing. And I'll explain the reason for these type signatures and this argument momentarily. And what we're going to do here is essentially take the first 4 chunks of the ciphertext according to our guessed key size. And I'm calling these chunks rather than blocks because we don't actually know that we are hewing to the correct block size here. So I don't want to lose generality, and I'm using a more general term than block, which is actually sort of a specific technical term. Now let me go ahead and import a helper function. And this will be familiar to anyone with a background in combinatorics. This function essentially does what you see in the example down below. It gives you all possible combinations of a given size, of a given number of elements. So we're going to use this to get all possible pairs of chunks from the tuple that we just built. And I'm using a tuple and not a list here because Python constructs tuples more quickly. It's not an important distinction, but it just seems worth mentioning. And the number of possible combinations of size 2 of 4 elements is 6. So we divide by 6 here. And then we are going to take this average Hamming distance between all 4 of our chunks, and we're going to normalize that by dividing against the conjectured size of our blocks. Now let's use this getScore function to score every candidate key size between 2 and max key size. And we could use a data class here rather than a tuple, like we did when we were cracking single byte XOR. In this case, it feels like overkill because these are not tuples that we're going to be passing around a lot. I suppose it would make the code cleaner, but I think this is fine, honestly. All right, now we have code to guess our key size. Let's proceed to... Actually, we're going to make a slight optimization against the textbook algorithm here. This one says that we should break the ciphertext into blocks and then transpose them, but we're actually going to skip straight to this step using Python's slice syntax. which is going to make things very easy for us. And just like the tuples up above, we are going to be scoring our candidate cracks and returning results as a two-tuple with the score and then the result. And this syntax here is the slice syntax that I was talking about. And this essentially works by saying, give me a slice of the string that starts at index I and then skips forward by jumps of size key size. So for example, you can see in this example, we get every other letter starting with the first one, the index at, or excuse me, the second one, which is at index 1. If I change that to a 3, then you see we get every third letter. And so by doing 0, 1, and 2 here, we can break these all up into the transposed blocks that are described on step 6 here. So that's what's going on there. And let's go ahead and import our crack XOR cipher function. And then we're also going to need to import the repeating key XOR function in order to decrypt our correct result. This is going to be another list comprehension. And we have to make sure to normalize this score again by the key size, because it's going to be worse for larger keys. And we will use a generator expression here to combine the single byte XOR keys from each of our guesses into a combined key here. And it thinks that these keys might be none. They actually can't be, but it doesn't know that, so we'll just tell it not to worry. And now let's go ahead and apply this. And rather than having an assert here, let's actually just let the user see that this works correctly. And then we'll also go ahead and add a little condition down here to explicitly exit the program if the Hamming distance function is not working as expected. And now, of course, the next step is to open up our input file, load the data from it as a string, and then convert that string to bytes via B64 decode, which we're going to have to import from standard lib here. And then we will call it get our ciphertext. And we're going to take 5 candidate guesses for the key size, and we're going to try our repeating key XOR cracking function against all 5 guesses. We're going to see which ones work. And this syntax just indicates that the score is a throwaway variable within this generator function. And this is where a data class actually would help out a little bit, because it's not obvious what indexing into these tuples does for us, or excuse me, tuple and list respectively, or list and tuple respectively, whatever the hell. Data classes would make this more readable, but it's fine. And this is going to be a fairly long plain text, so let's go ahead and decode it as ASCII. Rather than printing it out as bytes, this will ensure that things like new lines show up as expected, which might be helpful. Let's find out. And there we go. If we scroll up, we can see our guesses here, and there we go. Here's our best key, and here, of course, is our plain text. And our plain text is obviously correct as well, unmistakably so. So there you have it. There's challenge 6. I hope you enjoyed this video, and I hope you'll join me for the next one.